Example 1.18 is going to help us find the center of mass for a infinitely thin region in the plane. This is not going to be the centroid. This is not the center of the region. This is the center of mass when we consider a non-trivial density function. So let's walk through this. There's going to be a lot to it, so I'm going to zoom in quite a bit. And let's go ahead and sketch our region of integration. I am bounded above by the square root of x function, below by the straight line x divided by 2. And you can set these two functions equal to each other. In fact, I'm going to make my pen a little bit smaller. You can solve this. It becomes a quadratic. It has two zeros. One is going to be when x is equal to 0. That's right here. The other one is going to be when x is equal to 4. That's over here. Now, we don't want to integrate from 0 to 4. The problem specifies that we want to integrate from 1 to 4 between these two functions, and our density function is the quadratic x squared. So it's not really dense over here, but as we move away, it becomes more dense. Okay, so let's find this. In order to find centers of mass in 2 dimensions, we need 2 coordinates, an x center and a y center. Both of these are going to be found by taking moments and dividing by masses. So let's work on the x bar first, the horizontal center, which is going to use the moment in the y. In fact, I'm going to work on both of these first and solve for this total mass m. Let's go over here. Right, both of these centers require the total mass m, and we get this by integrating the density function, which is a function of x, which we stretch between the top curve and the bottom curve. And we integrate that with respect to x. Here, I will run through the integral. Our bounds of integration is 1 to 4. The density function is the x squared function. The top curve is the square root of x. The bottom curve is the 1/2 x function. All right, now I want this video to be focused on how to find centers of mass. I don't want us to get bogged down in the integration, so I'll skip a few steps. Once we distribute and integrate, I have an antiderivative of 2/7 x to the 7/2 minus a 1/8 x to the 4th, which I will evaluate between x is equal to 1 and x equal to 4. And when the algebra clears the room, we have 274 over 56 as a total mass. Now, back to our moments. The x-coordinate requires a moment in the y direction, which we obtain by integrating x times the density function times the difference in the two curves, f of x minus g of x. We will integrate from 1 to 4. X times my density function, I have a total of x cubed. Top curve, square root of x. Bottom curve, x over 2. After we distribute and find an antiderivative, we get 2/9 x to the 9 over 2 minus 1/10 x to the 5, evaluated between x is equal to 1 and x equal to 4. And when we substitute the upper bound and the lower bound and find the difference between those two, we have 1013 over 90. Now the y coordinate requires the moment in the x direction, which we obtain by integrating 1/2 times the density function times the difference of squares. We will integrate from 1 to 4. I have a 1/2 x squared. Square root of x, my top curve, squared is x. And the bottom curve, x over 2 squared, will give us a x squared over 4. After we distribute and integrate, we have an antiderivative of 1/2 times a 1/4 x to the 4 minus a 1/20 x to the 5, which we will evaluate between 1 and 4. And we obtain 63 over 10 as a result there. So I went through the integration pretty quick. Go back, pause the videos, and make sure you get the same things that I do. But the purpose of this video is to study centers of mass and not get bogged down in the integration. Our x bar, the horizontal component, will be the moment in the y divided by the total mass. So we have 1013 over 90 divided by total mass 274 over 56. Our y bar, the vertical component of the center, is found by the moment in the x divided by total mass. 63 over 10 divided by 274 over 56. So we can clean this up just a little bit. I have 5, 6, 7, 2, 8 over 2, 2, 2, 3, 0, and 3, 5, 2, 8 over 2, 4, 7, 0. Decimally approximated, we have 2.552 and 1.428, which puts our center of mass maybe somewhere right there.